She walked into the clinic without assistance. No cane, no walker, no one holding her arm. She sat down across from me, placed her hands flat on the table, and looked at me with eyes that were sharp and clear. Nothing about her presence suggested she was about to tell me she was 98 years old. I had been practicing medicine for over 4 decades at that point, and I had seen thousands of elderly patients. I knew what aging looked like. I knew what the body does when it has been alive for nearly a century. The slow gait, the thinning frame, the fragility in the grip, the way muscles seem to quietly disappear with each passing year, leaving behind a body that no longer responds the way it once did. She was none of that. When I reviewed her results, I had to check the name on the file twice. Her grip strength measured in ranges typically associated with women in their late 50s. Her muscle density scans showed almost no evidence of sarcopenia, the progressive muscle loss that, by her age, is not just common but medically expected. Her lean mass ratio, her walking speed, her balance assessment, everything pointed to a body that had somehow refused to follow the standard biological timeline. This was not a case of unusual genetics. I have been doing this long enough to know the difference. Genetics creates a ceiling, but it does not explain this kind of floor. The body does not preserve itself accidentally. Something was sustaining her. My name is Dr. Haruki Tanaka, and I have spent the last 40 years working in longevity and preventive medicine in Japan. I began asking her questions. Not the usual intake questions. I wanted to know everything. What she ate for breakfast, how she moved through her day, when she slept, who she talked to, what she had been doing for the past 7 decades without interruption. I recorded everything she told me, and as she spoke, a pattern emerged. Not a dramatic one, not a series of extreme interventions or unusual treatments. What I heard was a collection of small, consistent, biologically precise behaviors that she had maintained for most of her adult life. Behaviors that, when I looked at them through the lens of what we now know about muscle physiology, inflammation, and hormonal regulation in the aging body, were not random at all. They were, in fact, exactly what the science would have designed if you asked it to build a protocol for preserving muscle strength across a lifespan. I want to share what I found, not as a promise of any particular outcome, but as a medical account of what I observed and what the research says about why it works. If you are over 50, what follows will be directly relevant to decisions you are making right now, whether you realize it or not. If you find this kind of content valuable, the most useful thing you can do right now is subscribe and turn on notifications. I release new material regularly, drawn from clinical observation and peer-reviewed research. There are no shortcuts here and nothing is being sold to you. Just information as clearly as I can present it. Now let us begin with the first thing she told me, and the one that most directly contradicts what the majority of aging adults in the Western world are currently doing with their diets. Most people, when they think about protein and aging, assume the relationship is straightforward. Eat enough protein, maintain muscle. Eat too little, lose muscle. It sounds simple, and for younger adults it more or less is. But after the age of 60, this equation changes in a way that almost no one outside of geriatric nutrition research fully appreciates, and the consequences of misunderstanding it are severe. The process is called anabolic resistance. It refers to a measurable decline in the muscle's ability to respond to protein intake. In a younger person, a meal containing around 20 to 25 grams of high-quality protein is typically sufficient to trigger a meaningful muscle protein synthesis response, meaning the body uses that protein to build or repair muscle tissue. The signal is received, the machinery activates, the work gets done. In a person over 60, that same meal produces a significantly blunted response. The machinery is slower to start. The signal is weaker. The muscle does not receive the same instruction to rebuild. And if this continues across years of meals, 3 times a day, every day, the cumulative effect is exactly what we see in most elderly patients. Progressive, accelerating muscle loss that eventually compromises mobility, balance, and independence. What Mrs. Yamamoto, I will call her that for the purposes of this account, had been doing, entirely by habit and without any formal nutritional guidance, was eating protein in a way that partially circumvents this resistance. The first element was quantity per meal. She was not spreading her protein intake thinly across small portions throughout the day. Each of her main meals contained a meaningful concentration of protein. When I calculated the average, her lunch and dinner each contained approximately 35 to 40 grams of protein. Research out of Maastricht University and subsequently replicated in Japanese geriatric cohort studies has shown that in older adults, a per meal threshold closer to 40 grams is required to produce the same anabolic signal that 20 grams would produce in a younger person. She had reached that threshold not by design, but because her traditional dietary habits aligned with what the science would later confirm. The second element was source quality. She was not relying primarily on plant proteins or processed protein products. Her primary sources were fish, eggs, and fermented soy, specifically natto, which I will address in detail in the next section. These sources share a high leucine content. Leucine is the amino acid most directly responsible for activating mTORC1, the molecular switch that initiates muscle protein synthesis. Without sufficient leucine, the signal simply does not fire at the intensity required, regardless of total protein consumed. Fish, eggs, and fermented soy products consistently deliver leucine in concentrations that trigger this pathway effectively. The third element, and this one surprised me even with my years of experience, was timing relative to physical activity. She had a habit, lifelong, of eating her largest protein-containing meal within approximately 90 minutes of her afternoon walk. This is significant because muscle tissue is in a heightened state of insulin sensitivity and amino acid uptake during and immediately after physical activity. The window is real. Studies published in the Journal of Nutrition and the American Journal of Clinical Nutrition have both documented that protein consumed in proximity to muscle-activating movement produces meaningfully greater anabolic response than the same protein consumed at a neutral time. She was doing this every day without knowing the biochemistry behind it, simply because it was her routine. What I want you to understand about anabolic resistance is that it is not a fixed wall. It is a threshold that can be met with the right inputs. The muscle has not lost its capacity to respond. It has only become more demanding about the conditions required to respond. When those conditions are met consistently, the muscle continues to receive the maintenance signal it needs. When they are not met, when protein is too low per meal or leucine content is insufficient, or timing is completely disconnected from movement, the muscle slowly and silently receives no signal at all. Year after year, this silence accumulates into what we call sarcopenia. And by the time most patients become aware of it, significant and irreversible loss has already occurred. She had been sending the right signal 3 times a day for decades. That is not a minor variable. That is a primary explanation for what I found in her assessment. I want to talk about one food specifically because I believe it deserves more attention than it receives outside of Japan, and because the evidence supporting its role in muscle preservation is stronger than most people in Western medicine are aware of. Natto. If you are not familiar with it, natto is a traditional Japanese food made from soybeans that have been fermented using Bacillus subtilis var. Natto. It has a strong smell, a distinctive sticky texture, and a flavor that takes most people outside Japan some time to accept. It is not a food that tends to generate enthusiasm on first encounter. But what it contains and what those compounds do inside the aging body is medically remarkable. Mrs. Yamamoto had eaten natto almost every morning of her adult life. Not occasionally. Not as a health intervention she adopted later. Every morning, for decades, as a completely ordinary part of her breakfast. This is not unusual in many parts of Japan. Natto is a common breakfast food, particularly in the Kanto region. But what is unusual is understanding why this habit, maintained over a lifetime, would show up so clearly in her muscle tissue data. The first compound worth discussing is nattokinase. This is an enzyme produced during the fermentation process that has been studied extensively for its effects on fibrin degradation and microcirculation. What this means in practical terms for muscle tissue is improved blood flow to the capillary beds that supply muscle fibers with nutrients and oxygen. Muscle that is well perfused receives protein synthesis signals more effectively and clears metabolic byproducts more efficiently. In aging, microvascular dysfunction is a significant but underappreciated contributor to sarcopenia. Muscles can receive adequate protein in the blood, but if the microvascular delivery system is compromised, the amino acids do not reach the tissue at the rate required. Nattokinase, through its fibrinolytic activity, helps maintain the patency of these small vessels. The second compound is vitamin K2. specifically the -7 Malawian Quatches form, which is found in higher concentrations in natto than in virtually any other food source. Vitamin K2 in the -7 Malawian Quatches form has a half-life in the body of approximately 3 days, which makes it far more effective at reaching peripheral tissues, including muscle tissue and bone, than the shorter-acting -4 Malawian Quatches form found in some animal products. The role of K2 in bone density is reasonably well known. What is less discussed is its role in muscle function through the activation of matrix GLA protein, which helps regulate calcium handling in muscle cells, and through its relationship with osteocalcin, a hormone secreted by bone that influences both glucose metabolism and muscle performance. Research from Keio University in Tokyo has shown measurable associations between dietary K2 intake and preserved muscle function in Japanese elderly populations. The third element is the fermentation itself. Natto is not just a source of nutrients. It is a living food that contributes to the gut microbiome in ways that directly affect systemic inflammation. The Bacillus subtilis bacteria in natto produce spores that survive gastric acid and reach the intestine, where they compete with inflammatory bacterial strains and support the production of short-chain fatty acids that reduce intestinal permeability. Chronic low-grade inflammation, driven in part by a compromised gut barrier, is now recognized as one of the primary accelerators of muscle catabolism in aging. This is not a peripheral effect. Elevated inflammatory cytokines such as TNF-alpha and IL-6 directly activate pathways inside muscle cells that promote protein breakdown. A gut environment that keeps these signals low is a gut environment that protects muscle. Western geriatric medicine has largely not incorporated natto into its nutritional protocols because it is not a food with a Western cultural base, and because pharmaceutical and supplement research attracts more funding than fermented food research. But the Japanese geriatric literature is consistent. Studies from the National Center for Geriatrics and Gerontology in Obu, Japan, have tracked dietary patterns in elderly cohorts and repeatedly found that regular natto consumption correlates with better physical function scores, lower inflammatory markers, and reduced rates of sarcopenia diagnosis compared to elderly subjects with equivalent caloric and protein intake who do not eat natto. Mrs. Yamamoto did not know any of this. She ate it because her mother ate it, and her mother's mother ate it. The mechanism was invisible to her. The result was not. For those reading this who do not have access to natto or find the taste unacceptable, the compounds in question can be obtained through supplementation. Nattokinase supplements and -7 Malawian Quatches vitamin K2 supplements are commercially available and have been studied in isolation. But the food itself, in its fermented form, delivers these compounds alongside the microbiological benefits of live culture that a capsule cannot replicate. If access is possible, the food is preferable. If not, targeted supplementation of K2 -7 Malawian Quatches and nattokinase is a clinically reasonable alternative for adults over 50 who are concerned about muscle and vascular health. When I reviewed her physical activity history, I was not looking for extraordinary exercise capacity. I was looking for what she actually did every day without exception, and what she described was walking. This is not surprising. Walking is the most common physical activity among Japanese elders, and it is frequently cited in longevity research as a primary contributor to healthy aging. But the conversation I had with her about how she walked made me reconsider how much medical guidance about walking for the elderly is missing a critical variable. We tend to discuss walking in terms of duration and frequency. 30 minutes a day, 5 days a week, 10,000 steps. These metrics have value as general thresholds, but they describe quantity without any attention to structure. And in the aging body, particularly after 65, the structure of a walk determines whether it produces a meaningful muscular stimulus or simply maintains cardiovascular baseline without any significant effect on lower body strength. Mrs. Yamamoto lived in a neighborhood with natural topography. Her daily route, which she had walked for most of her adult life, included 2 sustained uphill segments. She described them casually. They were simply part of the path between her home and the market, and between her home and the community center where she spent time in the afternoons. She had not chosen them for their health benefit. They were simply where she needed to go. But the effect of those inclines on her lower body musculature over decades of daily repetition is not something that can be understated. Walking on an incline of even 5 to 8 degrees increases recruitment of the gluteus maximus, hamstrings, and soleus to a degree that flat surface walking does not. These are the muscle groups most critical to maintaining gait stability and fall resistance in older adults. They are also the muscles that atrophy most rapidly with sedentary behavior and that are most difficult to preserve through casual flat surface movement alone. Research from the University of Tsukuba's Institute of Health and Sport Sciences has examined how incline walking affects muscle fiber recruitment in adults over 65 compared to flat walking at the same speed and duration. The findings are consistent with what muscle physiology would predict. Incline walking activates type 2 muscle fibers, the fast twitch fibers responsible for power and stability, at significantly higher rates than flat walking. Type 2 fibers are the ones most vulnerable to age-related atrophy. They are the fibers that, once lost, are hardest to recover. And they respond to exactly the kind of stimulus that incline walking provides: controlled load, repeated contraction under resistance. The second structural element of her walking was pace variation. She did not walk at a single constant speed. She walked faster when she was on level ground and slowed when ascending. She sometimes paused, turned around, and retraced a short section. This is not a protocol, it is just how she moved through a real environment. But the effect of pace variation on cardiovascular and muscular adaptation is meaningfully different from the effect of constant pace walking. Variable pace walking produces intermittent spikes in heart rate and muscular demand that train both aerobic capacity and the neuromuscular system's ability to modulate force output. This kind of dynamic demand is something a treadmill at a fixed incline and fixed speed does not fully replicate. The third element was surface. She walked primarily on natural surfaces: stone paths, slight gravel, uneven pavement. Not exclusively, but predominantly. Uneven surfaces require continuous small adjustments from the ankle stabilizers, the peroneal muscles, and the deep intrinsic muscles of the foot. These are muscles that receive almost no training on flat, smooth surfaces, and their weakness in elderly adults is a primary contributor to ankle instability and falls. The proprioceptive demand of natural surface walking keeps these neuromuscular pathways active and responsive in a way that smooth indoor or treadmill walking does not. I am not arguing that walking on hills and uneven ground is a magic solution. I am presenting it as a structural observation. Her walking was not passive locomotion. It was, incidentally and unintentionally, a form of progressive musculoskeletal training. And it had been occurring daily, for decades, with no interruption. For those who live in flat urban environments or who have access only to smooth indoor surfaces, the practical implication is not complicated. Introducing any incline, a parking garage ramp, a staircase used as a deliberate incline walk, a slight hill in a park, for even 15 to 20 minutes of a longer walk creates the type 2 fiber recruitment stimulus that flat walking does not. The surface variety can be approximated with occasional outdoor walking on grass or gravel, even if most of the route is smooth. The pace variation can be introduced intentionally. Periods of faster walking alternated with moderate pace, without requiring any special equipment or training protocol. The point is that the form of movement matters as much as the fact of movement. And for the elderly body, the difference between stimulating and non-stimulating walking is not a matter of intensity or duration. It is a matter of structural demand. The conversation about meal frequency and aging is frequently dominated by intermittent fasting research, much of which is conducted on younger or middle-aged subjects and extrapolated to elderly populations in ways that the data does not fully support. I want to be precise about this, because the difference matters enormously for adults over 60 who are trying to protect their muscle mass. Intermittent fasting, typically involving 16 or more hours without caloric intake, produces a metabolic state in younger and middle-aged adults that can support fat oxidation, cellular autophagy, and in some protocols, improved insulin sensitivity. These are real effects with legitimate research behind them. I am not dismissing them, but the same fasting window in an elderly body activates a different set of biological responses, and those responses include accelerated muscle protein catabolism that is not offset by the anabolic rebound that younger bodies experience when eating resumes. The mechanism involves both IGF-1 and mTOR signaling. In younger adults, the anabolic response to protein intake after a fasting period is robust, mTOR activation is strong, protein synthesis rates spike, and the net effect is preserved or even increased lean mass. In adults over 60, this compensatory spike is blunted by the same anabolic resistance I described earlier. The muscle has reduced sensitivity to the synthesis signal, which means that even when food is consumed after an extended fast, the rebuilding response is insufficient to fully replace what was broken down during the fast itself. The net result, over weeks and months, is a slow but measurable loss of lean tissue. Mrs. Yamamoto ate 3 meals a day, every day without exception. Breakfast, lunch, and dinner. She did not skip meals. She did not have eating windows. She did not extend her overnight fast beyond approximately 12 hours, which is the natural result of eating dinner at a reasonable hour and breakfast within an hour or two of waking. This 12-hour overnight fast is not the same biologically as a 16-hour or 18-hour fast. It is a physiologically normal rhythm that allows for nightly cellular housekeeping without pushing the body into the muscle-depleting catabolic state that longer fasts produce in the elderly. Her meal distribution was also relatively even. She did not front-load or back-load her caloric intake dramatically. She ate a moderate breakfast, which included her natto, rice, and a piece of grilled fish, a moderate lunch, and a moderate dinner. This even distribution across 3 meals means that her muscles received a protein synthesis signal 3 times per day, each meal meeting or approaching the leucine threshold required to activate mTOR in the aging muscle. 3 activation events per day, every day across decades, is a fundamentally different biological environment for muscle maintenance than 1 or 2 larger meals would create. The research supporting this pattern in elderly populations is consistent. A 2019 study published in the journal Nutrients, examining protein distribution in Japanese adults over 70, found that subjects with more even protein distribution across 3 meals showed significantly higher appendicular lean mass than those with equivalent total daily protein intake concentrated in 1 or 2 meals. The muscle's response to the protein signal is not cumulative across a day. It is event-driven. Each meal is either a signal or it is not. Spreading those signals across 3 meals creates 3 opportunities per day for the preservation mechanism to activate. What I want to make clear is that the instinct many aging adults have to reduce their food intake, to eat less frequently, or to follow fasting protocols popularized by research conducted in younger populations is working directly against the biological reality of the aging body. The 60-year-old muscle is not the 40-year-old muscle. It does not respond to the same inputs. It does not recover from the same deprivations. Treating it as though it does is one of the most common and consequential nutritional errors I observe in my patients. She ate consistently, adequately, and at intervals that kept her muscle protein synthesis pathways active throughout each day. This was not a conscious health strategy. It was just how she ate, and it was one of the most protective things she could have done. Of all the variables I identified in Mrs. Yamamoto's history, sleep is the one I expected the least and that the research has most consistently validated since. She described her sleep in terms that were almost unremarkable in their regularity. She went to bed at approximately the same time each night. She mentioned the NHK Evening News as her cue, which runs at 9. She woke without an alarm at around 5:30 in the morning. She had no history of sleep medication use. She described her sleep as generally deep and uninterrupted, with occasional brief waking in the night that she said resolved on its own without difficulty. This describes 8 to 8.5 hours of sleep per night at highly consistent timing without pharmacological assistance. In the context of elderly sleep research, this is not typical. Studies in Japan and internationally consistently show that sleep duration and quality decline with age in most adults. Waking frequency increases, slow-wave sleep decreases, and circadian rhythm stability weakens. The consequences of this for the aging body extend well beyond fatigue. Growth hormone secretion follows a precise biological schedule. The majority of daily growth hormone release in adults occurs during slow-wave sleep, the deepest stages of the sleep cycle, typically reached in the first and third hours of sleep. Growth hormone is not simply a childhood hormone for physical development. In adults, and particularly in aging adults, it is one of the primary regulators of muscle protein synthesis and repair. It signals muscle cells to uptake amino acids and initiate rebuilding processes. Without adequate slow-wave sleep, this signal is diminished or absent. In adults over 60 who experience the typical sleep fragmentation associated with aging, frequent waking, reduced slow-wave sleep duration, shifted sleep timing, the consequence is reduced nightly growth hormone output. This means that regardless of how much protein they consumed during the day, the overnight repair and synthesis cycle that should consolidate the gains from those 3 protein signals is impaired. The day's work, metabolically speaking, is partially undone. Mrs. Yamamoto's sleep architecture, based on her self-report and the consistency she described, suggested she was accessing meaningful slow-wave sleep regularly. The stable timing was particularly significant. Circadian biology research has demonstrated that sleep timing consistency, going to bed and waking at the same time daily, is as important as duration for achieving deep sleep stages. The body's hormonal secretion patterns are time-locked to the circadian rhythm, and irregular sleep timing desynchronizes these patterns even when total sleep hours are adequate. Her NHK News routine was, incidentally, a form of chronobiological anchoring. The relationship between sleep disruption and sarcopenia is now well established in the research literature. A longitudinal study from the Japan Gerontological Evaluation Study tracking adults over 65 found that those with self-reported poor sleep quality had significantly higher rates of sarcopenia diagnosis at 5-year follow-up, independent of physical activity levels and dietary protein intake. Sleep quality predicted muscle loss beyond what diet and exercise alone could explain. This is because the nocturnal repair cycle is not optional supplementary work. It is primary maintenance. Daytime protein intake and physical activity create the conditions for muscle synthesis, but the synthesis itself largely occurs overnight during sleep. There is also a cortisol dimension to this. Fragmented or shortened sleep consistently produces elevated morning cortisol levels. Cortisol, in chronically elevated states, is a catabolic hormone. It promotes muscle protein breakdown as part of the stress response. An elderly adult with chronically disrupted sleep is running elevated cortisol signals that directly oppose the anabolic signals they are trying to create through diet and activity. The two systems are working against each other. She had, by maintaining stable, adequate sleep for most of her life, kept this cortisol interference low. I want to address a practical concern that many adults over 60 raise when sleep is discussed. They will say, correctly, that sleep becomes harder to maintain with age. This is true, and I am not dismissing it. But there is a meaningful difference between the natural mild changes in sleep architecture that come with aging and the severe sleep fragmentation that many adults accept as inevitable and do not attempt to address. Consistent sleep timing, a sleeping environment kept cool and dark, the avoidance of stimulant intake in the afternoon and evening, and limiting light exposure in the 2 hours before bed are not complex interventions. They are maintenance conditions for the biological processes that happen during sleep. They do not guarantee 8 hours of slow-wave sleep, but they create the conditions in which the body is able to access the deepest sleep it is capable of as regularly as possible. She had never been told any of this. She simply slept the way people in her community had always slept. Early, consistently, quietly, without interruption from screens or stimulants. And her muscles, year after year, received the nightly repair signal they needed. I want to turn now to something that receives far less attention in conversations about muscle preservation than protein and exercise, but which I believe is equally important for understanding her case. What she did not eat. This is not a discussion about restriction or willpower. I am not describing a diet defined by avoidance. I am describing the absence, across most of her adult life, of specific food categories whose mechanisms of harm are now well understood and directly relevant to muscle catabolism in the aging body. The first category is refined seed oils consumed in high quantities. She used very little cooking oil at all when she cooked. She used small amounts of sesame oil and occasionally olive oil. She did not use sunflower oil, corn oil, soybean oil, or canola oil as daily cooking fats. This is not uncommon in traditional Japanese cooking, which relies more on broth, steam, and fermentation than on fat-based cooking methods. The significance here is the omega-6 to omega-3 fatty acid ratio. Refined seed oils are high in linoleic acid, an omega-6 fatty acid that, in high dietary quantities, competes with omega-3 fatty acids for incorporation into cell membranes and serves as a substrate for the production of arachidonic acid, which is a precursor to pro-inflammatory eicosanoids, signaling molecules that promote inflammation. Chronically elevated systemic inflammation, driven in part by a high omega-6 dietary load, is now recognized as a direct activator of muscle protein degradation pathways, including the NF-kappa B pathway and the ubiquitin proteasome system that tags muscle proteins for breakdown. The second category is ultra-processed foods. She did not eat them because they were not part of her food environment or her habits. She cooked. She bought whole ingredients. She prepared food from recognizable components. The significance of this is not simply about nutrients. It is about what ultra-processed foods do to the gut microbiome and to systemic inflammatory markers. Research from the Instituto Nacional de Saúde Dr. Ricardo Jorge and from Japanese epidemiological studies both show that regular consumption of ultra-processed foods is associated with significantly elevated levels of C-reactive protein and IL-6, two inflammatory markers that directly correlate with accelerated muscle loss in elderly adults. The microbiome disruption from emulsifiers, artificial sweeteners, and other processing additives further compromises gut barrier integrity, increasing intestinal permeability and driving the systemic inflammatory load that muscles then pay for in accelerated catabolism. The third category is excessive added sugar. Her diet was low in added sugars not by design but by default. Traditional Japanese cooking does not rely heavily on sugar, and she did not consume sweetened beverages or desserts as regular daily habits. The relevance to muscle is through advanced glycation end products and insulin dynamics. High dietary sugar intake promotes the non-enzymatic glycation of proteins throughout the body, including structural proteins in muscle tissue. Advanced glycation end products accumulate in muscle and connective tissue and are associated with reduced muscle fiber elasticity, impaired mitochondrial function within muscle cells, and increased oxidative stress, all of which accelerate the deterioration of muscle quality independent of lean mass. Additionally, the insulin dysregulation associated with chronic high sugar intake interferes with the insulin-mediated glucose and amino acid uptake in muscle that is part of the normal post-meal anabolic signal. What I observed in her diet was not an aggressive nutritional protocol. She was not tracking macros or reading food labels. She was eating in a way that her culture and her upbringing had normalized simple, whole, minimally processed food, prepared at home, consumed in moderate portions at regular times. The absence of the three categories I described was simply the natural consequence of eating traditional Japanese food the way it has always been prepared. In clinical practice, when I see patients over 50 who present with early sarcopenia and whose dietary history I examine carefully, the pattern is almost always the same. Not simply insufficient protein. Sufficient protein consumed in a background of high systemic inflammation driven by seed oils, processed foods, and added sugars. The protein signal is trying to activate muscle synthesis, but the inflammatory environment is simultaneously running a degradation signal. The two cancel each other out. The muscle cannot receive a clear anabolic message in a body that is continuously receiving inflammatory instructions to break down. Her body was not receiving those competing instructions. The channel was clear. There is a dimension of her case that I initially noted but did not place at the center of my analysis, because it did not fit neatly into the categories of nutrition and physical activity that structured my initial review. But the more I examined the research, the more I recognized that dismissing it as lifestyle background would be a clinical error. She was socially embedded, deeply and routinely so. Every day, without exception, she had contact with other people in a structured, purposeful context. Not passive contact, not simply living near others. She walked to the community center in the afternoons. She participated in a small cooking group that met twice a week. She had a regular arrangement with 2 neighbors to share tea in the late morning. She was in contact with family members regularly. Her social interactions were not occasional social events. They were scheduled, repeating, and woven into the architecture of each day the same way her meals and her walks were. I want to explain why this matters biologically, because it is frequently discussed in wellness contexts in terms of happiness or emotional well-being, which leads people to underestimate its physiological significance. The first mechanism is cortisol regulation. Chronic social isolation in aging adults is consistently associated with elevated basal cortisol levels. I described cortisol's catabolic effect on muscle tissue earlier in the context of sleep disruption, but the same mechanism applies here. An elderly adult living in social isolation, a condition more common in Western societies than in the Japanese communities I have observed, is running chronically elevated cortisol that is directly promoting muscle protein breakdown every hour of every day. This is not a metaphor for stress. It is a hormonal signal with a measurable biochemical effect on muscle tissue. The second mechanism involves testosterone and DHEA. In aging women, testosterone, which is produced in small quantities by the adrenal glands and ovaries throughout life, plays a significant role in maintaining muscle protein synthesis and bone density. Regular positive social engagement has been associated in multiple studies with higher circulating testosterone and DHEA levels in elderly women compared to socially isolated counterparts. The mechanism is incompletely understood but involves the hypothalamic pituitary adrenal axis and the differential activation of stress versus social bonding pathways. When the nervous system is regularly in a social bonding state as opposed to a vigilance or isolation state, the hormonal environment shifts toward anabolic rather than catabolic signals. The difference in testosterone levels between socially engaged and socially isolated elderly women, while not large in absolute terms, is clinically meaningful for muscle maintenance over years and decades. The third mechanism is inflammatory cytokine activity. Loneliness, defined not as being alone but as the subjective experience of social disconnection, is now classified in the epidemiological literature as an independent risk factor for systemic inflammation. Meta-analyses of studies examining the relationship between loneliness and inflammatory markers consistently find that chronically lonely adults have elevated TNF-alpha, IL-6, and CRP levels compared to socially connected counterparts of the same age, controlling for diet, exercise, and other confounders. These are the same cytokines that directly activate muscle protein degradation pathways. Social disconnection is, through this pathway, a direct contributor to sarcopenia, not through behavior but through its effect on the inflammatory molecular environment of the body. Research from the Tohoku University Comprehensive Aging Research Center, which has tracked large cohorts of Japanese elderly adults in both rural and urban settings, has found that social engagement measures, frequency of social contact, participation in community activities, sense of social purpose, are among the strongest predictors of preserved physical function at age 85 and older, independent of baseline health status at enrollment. These findings have been replicated in Western cohorts, including data from the English Longitudinal Study of Aging and the U.S. Health and Retirement Study. Mrs. Yamamoto was not lonely. She was not isolated. She was embedded in a web of daily human contact that her community had built and that she participated in without any awareness of its physiological function. She went to the community center because she enjoyed it. She shared tea with her neighbors because it was pleasant and comfortable. The biological consequences of those interactions, the cortisol regulation, the hormonal environment, the anti-inflammatory effect, were entirely invisible to her. But they showed up in her lab results. When I look at everything Mrs. Yamamoto told me across those 2 appointments, the protein timing, the natto, the structured walking, the meal frequency, the sleep, the absence of inflammatory foods, the social architecture of her days, I do not see a collection of independent habits that each happen to be beneficial. I see a system. The word matters. Not a plan. Not a protocol. A system, meaning a set of behaviors that, together, address the same underlying biological problem from multiple angles simultaneously, such that each element reinforces the effect of the others and the overall outcome is greater than the sum of its parts. The biological problem of aging muscle can be reduced to 3 primary mechanisms. Protein synthesis declines because the anabolic signaling pathway becomes resistant. Inflammation increases because the body's regulatory systems become less efficient at resolving it. And the hormonal environment shifts away from anabolic signals, lower growth hormone, lower testosterone, higher cortisol, in ways that directly favor muscle breakdown over repair. Every behavior she had maintained across her adult life addressed one or more of these 3 mechanisms directly. Her protein intake and meal frequency addressed anabolic resistance. Her natto and her avoidance of inflammatory foods addressed chronic inflammation. Her sleep maintained growth hormone output and cortisol regulation. Her social engagement maintained the hormonal balance and suppressed inflammatory cytokines. Her walking provided the mechanical stimulus that keeps type 2 muscle fibers active and responsive. There was no redundancy in the system. Each element was doing work that the others did not fully cover. And crucially, no single element was doing enough alone. Her diet without her sleep would have left the nightly repair cycle incomplete. Her sleep without her physical activity would have maintained hormonal output without giving the muscle the structural stimulus it needed to trigger synthesis. Her activity without adequate protein would have created demand without supply. Her protein without the low inflammatory background would have been partially neutralized by simultaneous catabolism signals. They worked as a system because the problem they were solving is not a single cause problem. Sarcopenia does not arise from one deficiency. It arises from the convergence of multiple insufficiencies over time. The reason it progresses so quietly, and the reason most patients are not aware of it until significant loss has occurred, is that each individual contributing factor seems tolerable in isolation. A slightly insufficient protein intake, a slightly elevated inflammatory load, a slightly impaired sleep architecture, none of these, examined alone, would register as an emergency. But together, sustained over years, they produce an environment in which the muscle has no viable option except to decline. What she had built by habit and culture and simple daily consistency was the opposite of that environment. Her body had been receiving, for most of her adult life, the complete set of signals required for muscle maintenance, and none of the competing signals that work against it. This is the central medical observation I want to leave you with before we continue. Not that any one of her habits was remarkable in isolation. What was remarkable was the completeness of the system and the duration of its maintenance. The science does not require perfection. It does not require extraordinary inputs. It requires that the right conditions be present consistently, over time, without large interruptions. She had done that, not as a health project, as a life. And in the next part of this series, I will discuss what this means practically for people who are reading this in their 50s, 60s, and 70s, specifically, what the research says about how much of this system can be built or rebuilt at any point in adult life, and what the actual timeline for measurable improvement looks like when these changes are made consistently. The answer is more encouraging than most people expect, and it is grounded entirely in the physiology of muscle adaptation rather than in any motivational framework. If this account has been useful to you, I want to ask you directly to subscribe to this channel and to share this video with someone you know who is over 50 and who is thinking carefully about their health. Not because I am asking for your support in a general sense, but because the information I have presented here, the anabolic resistance threshold, the role of natto and K2, the structure of stimulating walking, the meal frequency data, the sleep physiology, the inflammatory mechanisms, the social biology, is not information that most people over 50 are receiving from their primary care providers. It is not being discussed in the standard medical appointment. It is coming from research that is being published, but not yet integrated into routine clinical guidance at the level that it deserves to be. The people who most need this information are not looking for it because they do not know it exists. You sharing this is the mechanism by which it reaches them. I release new material regularly, and each video follows the same structure as this one: clinical observation, mechanistic explanation, practical application, all grounded in peer-reviewed research and drawn from my direct experience with patients. There is nothing being sold. There is no supplement line attached to this channel. There is no program being promoted. The only thing I am asking for is your attention, and that you pass the information along. The next video in this series will be available shortly. I hope to see you there.